Hi, this is Janakareddy Dubbaka, Physics Rapid Revision for Neet and Mains. This is lecture number 1 from Atom. Here, Rutherford's nuclear model of atom. This model was proposed after the famous gold foil experiment by the Rutherford. In this experiment, alpha particles were emitted by a radioactive element. This is Bi 214 by 83 and was bombarded on a thin gold foil. This is the radioatomic source. From this alpha particles are emitted. These alpha particles are incident on a gold foil. These alpha particles are scattered from the gold foil and collected on the zinc sulfide screen. This is a zinc sulfide screen. We can collect that alpha particles on that zinc sulfide screen. Here the outcomes of this Rutherford experiment, most of alpha particles pass straight through the gold foil or suffer only small deflection. Few alpha particles, about 1 in 8000, get deflected through 90 degrees or more. Occasionally, an alpha particle gets rebound from the gold foil, suffering a deflection of nearly 180 degrees. See, for example, here is the atom. In that atom, this is the nucleus, the gold foil atom. Most of the alpha particles are undeflected, and some of the alpha particles are deflected like this theta, and some greater than 90 degrees. Only few can be reflected like this. This is 180 degrees. This is the outcomes of Rutherford model. In this impact parameter, see what is impact parameter means? Impact parameter is defined as perpendicular distance of initial path of alpha particle from the center of the nucleus. See, this is the central line of the nucleus. Alpha particle initial velocity vector is this one. This is the initial velocity vector direction. This is the central line. The perpendicular distance between initial velocity vector and the central line, that is nothing but a impact parameter. Here the formula for impact parameter, B is equal to 1 by 4 pi epsilon Z square by into cot theta by 2. Therefore, here E is nothing but energy of that alpha particle. Therefore, here important thing, here B proportional to cot theta by 2. See, some of the problems based on this one, B proportional to cot theta by 2. Here N be the scattered alpha particles depends upon angle of deflection, that is nothing but N proportional to 1 by sine to the power of 4 theta by 2. This is also very important relation. If you draw the graph, number of alpha particles scattered and a scattering angle, this is inversely proportional rectangular hyperbola. And the conclusions of Rutherford model, the positive charge was concentrated in a small region of the atom called nucleus. Here in alpha particle scattering, all the alpha particles, many alpha particles are undeflected, passing through the gold foil. Only few are deflected more than 90 degrees, that is 8001. Very few are reflected back per angle of scattering 180 degrees. That is the reason the total positive charge of the atom is concentrated at the center. That central part is called nucleus. It contradicted the Thomson prediction of uniform distribution of positive charge inside the atom. But according to Thomson model, here Thomson proposed that positive charge is distributed inside the atom, but here not distributed inside the atom. It is concentrated at a single point at the center of the atom. That central part is called nucleus. Negative charge particles, that are electrons, were revolving in circular orbits around the concentrated positive charge particles, that is protons, in the nucleus. Therefore, here electrons are revolving around the nucleus. These are the conclusions. Here limitations of Rutherford model, means the failure, that is one. This model does not explain the stability of the nucleus. Here, this is the nucleus. Electrons are revolving around the nucleus in a circular path. Any particle moving in a circular path, it is an accelerated motion. If a charged particle is accelerating, it emits radiation, means it emits energy. Therefore, it continuously emits energy. This energy will be lost, and finally, it rotate like this. Finally, fell into the nucleus. But it is not happening. Therefore, this thing is not explained by this Rutherford model. So, here, proton. This is hydrogen nucleus. An accelerated electron must spiral into the nucleus as it loses energy. This model does not explain the line spectrum of the atom. If this radiant energy, if you incident on any optical instrument, that is prism, we can observe a line spectrum, but it is here as a continuously emitting energy. This is continuous spectrum. Therefore, it does not explain the line spectrum. These are the drawbacks of the Rutherford model. Another one, distance of closest approach. Consider alpha particle is projected on the nucleus with kinetic energy k, and let d be the center to center distance between alpha particle and gold nucleus when alpha particle as it at its stopping point. Here, this is the alpha particle. When it is moving like this, its kinetic energy decreases, becomes at this point its kinetic energy equal to the interaction energy between these two. At this point, its velocity becomes 0. This minimum distance up to which it approaches the nucleus, towards the nucleus, that minimum distance is nothing but distance of closest approach. So here, for example, according to energy conservation, here initial kinetic energy plus initial potential energy, that is equal to kinetic energy final plus potential energy final. Initial kinetic energy I am taking k. It is at a large distance, therefore potential energy is 0. At this point, velocity becomes 0. Here, potential energy is nothing but means interaction energy. That interaction energy I am taking 1 by plus 1 by 4 pi epsilon q1 q2 by r. Charge of alpha particle is 2e, and the charge of the nucleus is Ze. That minimum distance is d. Therefore, here kinetic energy is equal to 1 by 4 pi epsilon 2 Z e square by d. This d is nothing but minimum distance, distance of closest approach. That d is equal to 1 by 4 pi epsilon 2 Z e square by k. Here k is nothing but initial kinetic energy. That kinetic energy is equal to half mv square. This is distance of closest approach. This is about Rutherford alpha particle scattering. But in problematic, the important thing is here, one is impact parameter, distance of closest approach. Next one, another atomic model, that is Bohr's model. Here in this rapid revision course, we have to concentrate only concept and formula based. First one, here postulates of Bohr's model. Bohr's first postulate state that electron in an atom could revolve in a certain stable orbits without the emission of radiant energy. Here, in this case, this is the nucleus Ze, and this one is the electron moving with velocity v. It is revolving around the nucleus. When it is revolving around the nucleus in a circular orbit, for this electron there must be some centripetal force. But a centripetal force always provided by an external agent. Here, centripetal force is provided by the electrostatic force between atom and nucleus. That electrostatic force, that is 1 by 4 pi epsilon. Charge of the nucleus is Ze, charge of the electron is E, here radius is r square, that is equal to centripetal force mv square by r. This is equation number 1, according to Bohr's first postulate. And the second postulate states that electron revolves around the nucleus only in those orbits for which angular momentum is some integral multiple of h by 2 pi, where h is Planck's constant. Therefore, angular momentum L is equal to nh by 2 pi. This angular momentum is mvr. Therefore, mvr is equal to nh by 2 pi. This is equation number 2. And third postulate, Bohr's third postulate states that an electron might make a transition from one of its specified non-radiating orbit to another of lower energy. When it does so, a photon is emitted having energy equal to energy difference between initial and final state. The frequency of emitted photon is given by nu is equal to delta E by h. For example, this is the higher energy state E2 and this is the lower energy state E1. When electron transition takes place from higher energy to lower energy, here a photon is emitted, that photon of energy h nu. Therefore, this h nu is equal to energy difference E2 minus E1. Therefore, nu is equal to here E2 minus E1 by h. This is the frequency of emitted photon. Next, from equation 1 and 2, we can directly write down this radius of nth orbit. Here, radius of nth orbit Rn is equal to n square z square epsilon naught by z pi me square. There is no need to remember all these things. Here, important thing, radius in nth orbit 0.53 n square by z angstrom. This is the important formula. For example, n is equal to 1. Here n is equal to 1. For hydrogen like atom, z is equal to n. Therefore, R1 is equal to 0.53 angstrom. This is called Bohr's radius. Here, this radius of nth orbit proportional to n square by z. Another one, radius of nth orbit inversely proportional to mass of the electron. Here, this one is very important. Rn proportional to n square by z. See, how can you remember this one? One simple thing. I am writing here, run n2 z. Run n2 z. Run means r. Here n. This is z. Means r proportional to, this is n square by z. You have to remember like this. See here, run n2 z. Therefore, this is r. Here is n. This is 2. This is z. Therefore, r proportional to n square by z. Another one, velocity in nth orbit, that is Vn is equal to Ze square by 2nh epsilon naught. Here also there is no need to remember all these things. Here also you have to remember velocity in nth orbit, that is 2.19 into 10 to the power of 6 into z by n. Z by n. Therefore, here Vn proportional to z by n. Here Vn proportional to z by n. See, how can you remember this one? This for a simple thing I am taking Vazan. Therefore, here Vazan V z n. Therefore, V proportional to z by n. V proportional to z by n, that is Vazan. Vazan means weight. Like that, frequency f, fn proportional to frequency f proportional to z square by n cube. Frequency or angular frequency omega proportional to z square by n cube. Like that, time period is inversely proportional to omega. Therefore, time period proportional to n cube by z square. This is about radius in nth orbit, velocity in nth orbit, angular frequency in nth orbit, time period. Next one, energy of an electron. Here energy, the potential energy Un is equal to minus m e to the power of 4 z square by 4 pi epsilon naught. this is the kinetic energy, and this is the total energy. See here, potential energy, this is the total energy, this is the kinetic energy. See here, kinetic energy and potential both are same. Here kinetic energy m e to the power of 4 z square by 8 pi epsilon 0. Here also same thing, but here a negative sign. Therefore, kinetic energy and potential and total energy both are same in magnitude but opposite direction. Kinetic energy never be negative, always positive. Here potential energy, here 4. Therefore, the relation is total energy is negative of kinetic energy, that is un by 2, that is potential energy. Therefore, potential energy 2 times of total energy. Potential energy is 2 times of total energy, and total energy, kinetic energy both are same in magnitude. Same in magnitude. If anything, for example, any orbit, the ratio between potential energy to total energy is 2:1. Any orbit, the ratio between potential energy to total energy is 2 by 1. This is about another important thing. Here total energy E is equal to minus 13.6 z square by n square electron volt. This is one of the important formula for this chapter. See here also total energy proportional to z square by n square, and also total energy proportional to mass. See, for this total energy, this is the total energy. For this one, I'm multiplying with CH, dividing by CH. See, after that one, this term is nothing but CH cube, Rydberg constant. This Rydberg constant is 1.09 into 10 to the power of 7. Therefore, this is Rydberg constant R. Here is the CH, Z square by N square. Therefore, RCH value minus 13.6. Therefore, energy, another form, one is En is equal to minus 13.6 Z square by N square, or En is equal to minus RCH into Z square by N square. This is another form. This RCH is nothing but 13.6. Here R is called Rydberg constant. That value is 1.09 into 10 to the power of 7 meter inverse. This is the total energy. See here, this is the energy diagram. N is equal to 1 level. Here N is equal to 1. For this N is equal to 1, energy is minus 13.6. N is equal to minus 3.4. N is equal to 3, minus 1.51, minus 0.85, minus 0.5, up to infinity level, this is having 0 energy. Therefore, infinity level having the highest energy, 0, it is negative. And the energy difference between first and second is 10.2. In some problems, we will directly substitute whenever a photon of energy is given 10.2, means that photon can excited from ground state to n is equal to 2. Therefore, energy difference between 1 and 2 is 10.2. Energy difference between 2 and 3 is 1.89. Energy difference between 3 and 4 is 0.66. Another important thing, here kinetic energy is proportional to 1 by R, it is positive. When you moving from lower energy level to higher energy level, lower energy level to higher energy level means radius increases. When radius increases, kinetic energy decreases. When kinetic energy decreases, potential energy increases and total energy also increases. You have to remember only for kinetic energy. If kinetic energy increases, potential energy, total energy, this one decreases, this one increases. For example, when it is de-excitation from higher energy level to lower energy level, higher energy to lower energy means R decreases. When R decreases, kinetic energy increases, then potential energy, kinetic energy, potential energy, total energy decreases. This is a very, very important one. You have to consider only kinetic energy. Based on kinetic energy, you have to find out what is the change in potential energy and total energy. If kinetic energy increases, potential and total energy decreases. If kinetic energy decreases, total energy and potential energy increases. But here, kinetic energy inversely proportional to 1 by r. As r increases, kinetic energy decreases. As r decreases, kinetic energy increases. This is the energy diagram. Next one, excitation energy. The excitation energy of an atom is defined as energy required by its electron to jump from the ground state energy to any one of the excited state. For example, here electron should be excited initially from ground state to any state. That energy needed is nothing but excitation energy. For example, in one electron is in ground state, it is excited to second level, that is n is equal to 2. In that case, excitation energy E2 minus E1. Excitation potential, the value of potential difference across the electron for which the electron must be accelerated from rest so that its kinetic energy is equal to excitation energy of the electron. Means very simple, excitation potential is excitation energy by E. Therefore, E2 minus E1 by E, that is nothing but voltage. E2 minus E1 by E, here when it is excited to first to second level, then that E2 minus excitation energy by E is called excitation potential. Here another important thing, other than ground states are called excited states. N is equal to 1 is nothing but ground state. N is equal to 2 for first excited state. N is equal to 3 for second excited. This is very important. Whenever any problem, second excited state is given, we have to substitute in the place of n, that is 3. Third excited means n is equal to 4, like that. This is excitation energy. What is ionization energy? The minimum energy required to remove an electron from atom is known as ionization energy. See, for example, electron is any energy level. If you want to remove that electron to infinity, the energy needed is nothing but ionization energy. Therefore, ionization energy is E infinity minus En. Generally, here at infinity, energy is 0. Therefore, ionization energy, that is equal to En means minus 13 point En is equal to minus 13.6 Z square by N square. Here E ionization is nothing but E infinity 0 minus En, minus into minus plus, therefore 13.6 Z square by N square. Same thing, ionization potential, ionization energy by E is called ionization potential. Here binding energy means the minimum energy required to bound the electron from the nucleus is called binding energy. The binding energy is negative of ionization energy. So here binding energy is equal to negative of ionization energy. Ionization energy is generally positive. Therefore, if you put minus here, this is nothing but a binding energy. Next one, here this is very important. Line spectra of hydrogen atom. See, whenever any electron is excited from ground state to another energy level, it is de-excited to lower energy level. During the de-excitation, it emits a photon of energy. Here in this hydrogen spectrum, there are different spectral lines. This is when n is equal to 2 to n is equal to 1. Therefore, from here n is equal to 1, this is lower energy level. From higher energy level to n is equal to 1, this is called Lyman series. This is in ultraviolet emission. And this is Balmer series. Therefore, initial energy level, final energy level is 2. Here, final energy level is 1. For 2 Balmer series, 3 Paschen series, 4 Brocket series, 5 Found series. These are the different spectrum and hydrogen, different spectral lines in hydrogen atom. Lyman series, Balmer series, Paschen series, Brocket series, Fund series. This is in ultraviolet region, visible region, infrared region. This is a far infrared region. This is also far infrared region. Here, whenever the electron de-excitation takes place, wavelength formula very important. 1 by lambda is equal to r z square into 1 by n final square minus 1 by n initial square. This is very, very important one. Here, in every series, spectral series, this Lyman series is there. In this Lyman series, the first line is having maximum wavelength. Last line is called minimum wavelength. We have to remember that this length is minimum. Length minimum, therefore maximum wavelength. Length maximum, minimum wavelength. In some cases, minimum wavelength also called as a limiting wavelength. Therefore, you have to find out what is the maximum wavelength in Lyman series, minimum wavelength in Lyman series, and also we have to compare our ratio between maximum wavelength in Lyman series, minimum wavelength in Paschen series. There is a confusion which one is first line, second line. For that, what is the final energy level? For that, I am going to give one a tip here. Using that one, we can find out any line wavelength. That is, they are very, very important. See like then, low BP, high BP, low BP, high BP. After that, round up this H. Here, two P's are there, two P's are there. One is Balmer series, another one is Brocket series. In alphabet, first letter is A, therefore, here is A, this is R. Same as in Paschen series also, this one is PA, this is P. After that, give the numbers 1, 2, 3, 4, 5. These are the numbers. In our wavelength formula, 1 by lambda is equal to Rz square, 1 by n final square minus 1 by n initial square. See, in this formula, n final is our number. For example, Lyman series, n final is 1. For all, for example, if it is first line, second line, maximum wavelength, minimum wavelength, any wavelength, n final is 1. N final is 1. For example, what is the maximum wavelength in Lyman series? First line is the maximum wavelength. Therefore, in our Lyman series, n final is equal to 1. Whenever transition takes place from 2 to 1, 1 above the 1 there is a 2. Therefore, 2 to 1 is first line, 3 to 1 is second line, 4 to 1 is third line, like that. Last line means infinity. Therefore, n initial is equal to infinity. That is nothing but a minimum wavelength in any series. If you remember this one, we can compare or we can find out maximum wavelength or minimum wavelength. Also, we can compare the wavelengths. This is very, very important. Low BP, high BP. Therefore, there is no H in our series. Therefore, Lyman series 1, this one is Balmer series 2, Paschen series 3, Brocket series 4, Fund series 5. But in our wavelength formula, n final is our given number. In that series, maximum wavelength means whatever the number is given, 1 above this one. Therefore, 1 means it is from 2 to 1, 2 means it is 3 to 2, 3 means it is 4 to 3, 4 means it is 5 to 4, 5 means it is 6 to 5. That is nothing but maximum wavelength. Minimum wavelength means infinity. See, infinity to 1, minimum wavelength. Infinity to 2, minimum wavelength in Balmer series. Infinity to 3, minimum wavelength in Paschen series. Infinity to 4, minimum wavelength in Brocket series. Infinity to 5, minimum wavelength in Paschen. Like that, we can compare any wavelength is given. Another important thing, whenever electron is excited to higher energy level, during de-excitation, it emits a photon. The number of spectral lines and number of photons emitted, that is equal to n into n minus 1 by 2. For example, if it is excited from ground state to fourth excited state means n is equal to 5. Put n is equal to 5 here. 5 into 5 minus 1 by 2. Therefore, 5 into 5 minus 1, 4 by 2, 2. Therefore, 10 spectral lines can be emitted. This is very, very important. This is number of spectral lines emitted, n into n minus 1 by 2. This is the complete theory of atom. It's a very, very limited syllabus and also very few formulas. So this chapter is very important. No lengthy concepts, more concepts or simple concepts and simple formulas, then we can answer any question is given from this chapter.